Look at this visual representation of raw data. Artificial neural networks are engineered to process chaotic, high-dimensional datasets like this. In mathematics, we call them universal function approximators because they can compute and map nearly any imaginable process, conforming to highly irregular realities. At the lowest level, this complexity is built on very simple math. Each node inside a network takes incoming data, calculates the sum of those inputs multiplied by specific weights, and then adds a bias. This diagram outlines the standard architecture. Raw information enters through the input layer, pushed directly into the hidden layers. It's assumed that depth equals intelligence, that simply stacking hundreds of these interconnected layers automatically gives the network the capacity to learn complex nonlinear patterns. But the mathematics of purely linear functions dictate otherwise. If the nodes are simply multiplying and adding, every single calculation passing through those connections remains strictly linear. Without a mechanism to break that linearity, a deep neural network collapses mathematically. No matter how many hidden layers you stack, it operates exactly like a basic linear regression model, entirely incapable of deep learning. Isolating a two-layer network, the first hidden layer's output is a linear equation. If fed directly into a second layer, it substitutes the first equation as its input. Algebraically simplified, the terms combine, collapsing into a single linear equation with new constants. The output is still just a polynomial of degree 1. Adding the second layer changed the numbers, but it didn't change the shape of the function. 10, 50, or 1,000 linear layers will always reduce to the equivalent of a single layer. This scatterplot shows why that matters. Real-world data, like images or audio, is deeply entangled. If you try to draw a straight linear boundary through these interlocking spirals, you fail to separate the categories accurately. The engineering solution is to apply an activation function, a scalar-to-scalar transformation, immediately after the weighted sum is calculated inside every single node, before passing the signal to the next layer. By injecting these mathematical curves at every juncture, we stop the equations from collapsing. This nonlinearity is the exact mechanism that gives the network the flexibility to mold its boundary to the specific curvature of the data. Early neurocomputers and artificial networks relied heavily on what are known as squashing functions to provide this nonlinearity. The most prominent among them was the sigmoid function. This is the sigmoid curve. Geometrically, it takes any input value, from -infinity to +infinity, and squashes the amplitude of that signal into a strict probability range between 0 and 1. To understand why it was used, we have to look at how networks learn. After a network makes a prediction, it measures the error and updates its weights to improve. It does this using an optimization strategy called gradient descent. Gradient descent relies on backpropagation, which means the network has to calculate derivatives backward through the layers. For this calculus to work, every activation function used in the network must be continuously differentiable. Sigmoid fits this requirement perfectly. It forms a smooth S-shape where the derivative is precisely defined at every single point. Engineers also developed alternatives like the hyperbolic tangent, or tan function. It is mathematically similar to sigmoid, but it maps values between -1 and +1, which solves sigmoid's problem of strictly outputting positive numbers. These squashing functions provide elegant, differentiable curves. But forcing dimensions of input data into tiny, finite numerical boundaries introduces a mathematical bottleneck when the network scales. Watch the geometry at the extreme tails of the sigmoid curve. As the input values become very large or very small, the curve flattens out. The tangent line representing the derivative approaches a slope of exactly 0. In calculus, the slope represents the gradient, and the gradient dictates the rate at which the network learns. A flat slope means the learning rate is infinitesimally small. Backpropagation uses the chain rule. It calculates the final error, finds the derivative of the output layer, and sequentially multiplies that derivative by the derivative of the layer before it, chaining all the way back to the start. This exact mechanism exposes the critical vanishing gradient problem. Because squashing functions produce derivatives that are extremely small fractions, multiplying them together sequentially causes the total gradient to shrink exponentially. Looking at the architecture diagram, you can trace the impact. The error signal starts strong at the output, but as it moves backward through the hidden layers, The chained fractions make the signal progressively smaller until it essentially disappears. By the time the backpropagation reaches the earliest hidden layers, the gradient is effectively zero. Sigmoid functions inadvertently paralyze the front of the network, preventing the deepest weights from updating and stalling the training process entirely. To build deeper, more complex architectures, researchers had to move beyond squashing functions. The solution they found was the rectified linear unit, widely known as ReLU. This chart displays ReLU's piecewise math. It returns the maximum between 0 and the input x. If the input is positive, it returns the exact same value. If it's negative, it returns exactly 0. This solves the vanishing gradient purely through its geometry. On the positive side of the axis, the slope is a straight 45-degree angle. That means the derivative is always exactly 1. When backpropagation chains those layers together, multiplying by 1 preserves the gradient's full magnitude. ReLU sacrifices the mathematical smoothness of a curve for sheer efficiency. Because it forces negative values to 0, it also means not all neurons are activated at the same time, making the computations much lighter. But the function carries a severe operational flaw. If the linear transformation from a node drops below 0, the function outputs a flat horizontal line. Here, the derivative is 0. This severe operational flaw creates the dead neuron phenomenon. If a node falls into this negative space during training, the 0 gradient permanently halts any future weight updates for that node. When this happens, the specific node stops learning entirely. Engineers developed immediate patches for this. Leaky ReLU alters the negative side of the function, assigning an extremely small linear component, like 0.01 times x, so the gradient never hits absolute 0. Further iterations pushed this even further. Parametrized ReLU allows the network itself to learn and adjust the angle of that negative slope, while exponential linear units apply a log curve to the negative values. Deep learning engineers willingly abandoned the elegant calculus of Sigmoid for the harsh angles of ReLU. They realized that preserving the gradient across deep architectures is vastly more important than curve smoothness. The search for the optimal activation function remains an active area of study. Recently, researchers at Google discovered a new alternative called Swish. Swish is mathematically defined by taking the input value, x, and multiplying it by the sigmoid of x. Looking at the Swish plot, there is a unique geometric identifier that separates it from standard ReLU. Notice the specific segment where the line dips slightly below the 0 axis before sweeping upward. Mathematically, this makes Swish a purely non-monotonic function. Unlike the others, the output value of the function can actually decrease momentarily, even while the incoming input values are strictly increasing. In certain complex architectures, Swish frequently outperforms ReLU. This performance gap drives ongoing research into more specialized scalar transformations. Translating these mathematical properties into an actual functional model requires strict engineering rules. You have to assign specific functions to specific locations in the topology. The first rule of modern architecture: always utilize ReLU or its leaky variants for the inner hidden layers. Applying ReLU here guarantees fast computational training and actively defends the network against gradient death across long backward passes. The second rule: reserve squashing functions exclusively for the final output layer. For example, if the network is categorizing data into multiple classes, it uses a SoftMax activation function on those final output nodes. SoftMax combines multiple sigmoids to translate the raw, unbounded scores from the hidden layers into clean probabilities that equal exactly 100%. Raw information flows in, gets aggressively mapped by the ReLU-driven hidden layers to preserve learning speed, and is finally squashed into a readable probability at the exit. Prediction accuracy depends on the engineering of these scalar-to-scalar transformations. These node-level calculations provide the flexibility required to map the underlying structure of chaotic data.